Alright, so this is problem 4 from exam 3. So I've tried to reproduce the slope fields here, but obviously there's a lot less detail than the pictures that were given to you on the exam. So I suggest that you refer to the exam paper so that you can see more clearly what the slope field looks like. But I have tried to capture at least the essential features of each of these so that we can discuss how we match each differential equation to its slope field. So let's take a look at this one first. The main thing to notice here, I think, is that as we move along a line like this, so where y is equal to 2x, the slope is always equal to 0. And that tells you that this one is going to be y prime equals 2x minus y, because this is the only one of the equations given to you that has that property. So I think that's the easiest way to recognize it. Of course, you can also check the slopes in the other regions are consistent with this choice. Also, this is maybe the hardest one to identify, so you could also just leave it for last and just use process of elimination. This one is actually probably the easiest one to identify. So the reason for this is because you notice that in all of the other pictures, sometimes the slope is positive, sometimes the slope is negative. In this one, however, the slopes in our slope field are always positive. The only one of the differential equations given to us that has that property is y prime equals e to the xy, because we know the exponential function is always positive. So that lets us identify this one. Now let's look at the last two. So here, this one, we see that whenever y is positive, the slope is positive. Whenever y is negative, the slope is negative. If you look at the differential equations that are available to us, the only one that has that property is y prime equals x squared y. So that leaves, of course, this one has to be y prime equals negative y, and we can do a similar reasoning here as we did for part C, which is that if y is negative, the slope is positive. If y is positive, the slope is negative, and we can see that's consistent with this differential equation. So that, I think, is sort of the easiest reasoning that I can think of, at least, to explain how to match each of these differential equations up to its slope field. Of course, another thing you could do is just pick some random points and check with the different equations and see if you can sort of sketch your own slope fields and then which ones do they match up with. But that's a bit more time consuming. So this was part A of the problem. Part B asks us to identify which of these is separable and then solve them using separation of variables. So y prime equals 2x minus y is not separable because we have this subtraction sign here, so we could add y to the other side, but then it wouldn't be something dy equals something dx. This one also is not separable because even though we have a product of x and y, it's in the exponents. There's no way to divide through by all the y's and get them over on the left. This equation, however, is separable. So y prime equals x squared y is separable. So let's solve it using separation of variables. We divide through by y. We'll get 1 over y dy antiderivative is equal to antiderivative x squared dx. If we calculate these antiderivatives, we'll get natural log absolute value of y is equal to 1/3 x cubed plus c. Let's exponentiate both sides. We'll get the absolute value of y is equal to a new constant a, which will be e to the power c, times e to the 1/3 x cubed. And then we can absorb the absolute value into the constant to just get that y equals a e to the 1/3 x cubed. Then our last equation is y prime equals negative y. This one is also separable. So let's try to solve this one with separation of variables as well. This one is a little bit easier, so let's do the same procedure. Move the y to the left, the dx to the right. So we'll get 1 over y dy antiderivative equals negative antiderivative of just 1. So if we take the antiderivatives, we'll get log absolute value of y is equal to negative x plus some constant. Exponentiate and drop the absolute value sign, and we'll get y equals ae to the negative x. And of course, because this is an equation we're familiar with, we already studied it earlier in the class, we know that this is indeed the correct solution to that equation.